And I must thank you for organizing these smooth transport facilities from the train to all these, all these communication to email and all these things. So it was, I would say, it was quite nice arrangement. So thank you thank you members also for giving me chance to speak here about my job talk. So the first part is this actually this teaching job. So I have chosen actually my PhD on basically coordination chemistry. So this is I will start with bonding theories in octahedral transition metal complexes, right? So of course, why of course from the bachelor or master's level also you should understand or you should ask questions why you should particularly want to understand or read some things. So coordination compounds, let's say transition metal complexes, they have immense roles in studying from biology. From here, at least from if you can say hemoglobin, this is the red blood cell oxygen transport carrier. So this is the deoxyhemoglobin and this is oxyhemoglobin. You can consider these are coordination compounds. Or cisplatin, this is a anti-cancer treatment reagent. So coordination compounds are also in medical use. Now, this is the first manganese acetate complex with 12 manganese and oxygen 12. So this is the molecular formula. But the thing is that this is first single molecular magnet, so compound. So this single molecular magnet is also important in basically understanding a lot of basic magnetic property also. Or they have important applications in spintronics or other field. But this is a photoredox catalysis. So this is also a coordination compound. So this basically, if you excite with light in the it attacks a catalyst. So my point is that you should understand the coordination compound in one aspect. And so the main part is the bonding theories, right? So I will be speaking today about octahedral transition metal complexes. So when I speak, let's cobalt hexa amine chloride complex. So I can just, when I will be speaking, you can, in general notation is that you omit the counter anion when you speak about the coordination compound. Now this is octahedral. Now when Cartesian coordinate, you can do it this way. So this is z-axis, this is x, and this is y-axis. So when you want to speak about particular geometry, you must have the Cartesian coordinate in your mind. Now, I will be talking about crystal field theory mainly today. So, but crystal field theory there was previously by Linus Pauling in 1931. I think he proposed that valence bond theory was widely used, and this basically, it is based on the hybridization of the empty d and sp orbitals of the metal ion. But the valence bond theory was not able to explain magnetic properties, the color of the complexes, or the bond length differences. That's why this crystal field theory came in mind. And this was originally proposed by Hans Bethe in 1929. Later, Van Vleck actually modified it, because this is, I will show you, it is actually electrostatic interaction between metal and ligand. But Van Vleck, he modified it. He took the metal ligand covalent interaction into the mind, and it is his theory. Actually, the ligand field theory, or let's say MO theory, is the most advanced theory, which is I think known in textbook. Also, I also know that this is the most theory which is able to explain most of the things. This also able measure of the things, but not most of the things. So this is actually, I must say, this is octahedral. This plane, equatorial plane, and this is called axial positions, is ligands. So in the geometry, octahedral geometry is, you should read like this. Now, when I will copy octahedral, there are in the periodic table, there are 3D series, 4D or 5D series. So from scandium to zinc, these are the 3D, 4D is yttrium to cadmium, and then lanthanum to mercury is a 5D series. But mainly whatever we propose in theory is 3D series. So next, so of course any theory has a basic, postulates, basic concepts are there. So what is let's say ligands is the point like negative charges. So and metals are the point like positive charges. So in the result is an electrostatic attraction between them, interaction. Now no covalent interaction. This is the theory. And when you apply particular field, octahedral or tetrahedral or square planar, you will have different geometry and different degeneracy lifting of the d orbitals. So let me first tell you that how when you want to study the octahedral geometry or 3D transition, you should know the shapes of the orbitals. So we see this DYZ, DXZ, and DXY. This is a 3D view, it's a clear-cut view. So you can see that the lobes are in between the axes. Now in the dx square minus y square and dz square, the lobes are along the axis. So if you draw again, and you can, I think in the notebook also you can just extend the axis and you can draw this dxy, dxz, and dyz. So if you consider this plane and xyz axis, when free metal in the vacuum, this is the energy. And when ligand approaches the metal ligand electron, because electron repulsion will happen, so energy will be raised. So this is if you consider a spherical field like a football, in the center there is a metal and ligand can approach at any side, the energy of the orbitals will be equally affected. So this is a spherical field, or some book it is called also free-splitting condition. Now when you apply this octahedral ligand approaches, from this 4 ligands from this equatorial plane, 2 ligands from the axial plane. So what happens there? This x square minus y square and dz square orbital are the affected more because they are facing the direct approach of the ligand. As a result, the energy will be raised. Now this center is actually called barycenter. So when some orbital energy is raised, in order to conserve the energy, the other orbital energy will also be lower. So because this has no direct facing with the ligand, that's why these orbitals energy will be lower. Now this difference in between the T2G and EG orbital is termed as 10 dQo. O is for octahedral. I will come what is 6 dQo and 4 dQo. So 4 dQo is the basically the energy of each T2G electron, and 6 dQo is the energy of each EG electron. Now, if for the d orbitals, as you know all, the maximum 10 electrons can be accommodated. And so, next, why are you? Okay. Okay.
So, just now you said these are like the point electrons.
Yeah.
Yeah. You are also showing me that these are actually distributed charge distributions. They are not point charges.
I mean, when you apply the octahedral field, you have to apply a particular geometry, right? When you want to construct the octahedral field, now that is not spherical. That has some axial and equatorial.
So there is a distribution.
Yeah.
On the one hand, you are saying it is like the metal is like a positive charge, a point charge, when the ligand is under point charge. Therefore, they interact as though they are columbic.
Yeah.
And so you are also showing me these orbitals.
Yeah.
Which is telling that the charge in substance is distributed. It's not a point.
It might also.
How do I reconcile these two? On the one hand, we told that we point charges and we develop a model. But then we also have these orbitals, which are not spatially localized. They are distributed.
Yeah.
You can come later. In case something you can tell me.
Okay. Already I understand. Okay. Can I move?
Yeah, please.
So 10 dQo, this is the difference between the T2G and EG orbital electrons in the octahedral field. So how do we get this? Now, if you consider total 10 electron maximum, it can be accommodated. You consider that E is the energy of each electron. So then 10 E equal to 4 dQo is the T2G, it is stabilized, and this is destabilized. So then 4 into E plus X, I mean, this is total 4 electron can be here. Since it is destabilization, it is converted as a plus X, and 6 electron maximum here. So this is stabilized, that's why minus. So if we consider solve this equation, you get 2x equal to 3y. Now we know that x plus y equal to 10 dQo, and in that way we get this. This is 6 dQo, x equal to, and y equal to 4 dQo. That's how this energy term come from this simple solving of this problem. Next, of course, this is an important fact is that what is the octa delta O value? This octahedral ligand splitting energy, how it depends on some certain factors. Obviously, it depends on oxidation state of the metal ions, position of the metal ion in the periodic table, exchange energy, metal ions of a particular period. But I will talking also oxidation state of the metal ion. This is adopted from a book, and this unit is kilokaiser. This is equal to 1000 centimeter inverse. So if you see that when you increase the oxidation state, the octahedral ligand field splitting energy increases. Because why? Because the ionic size is decreasing, the metal ligand bond lengths are getting shortened, and more interaction is happening. So they will repel each other. As a result, the delta value will increase. And same thing for the cobalt complex also. As you can see, when the cobalt 3 complex or cobalt 3, when the oxidation state is higher, you get delta value higher. Next, position. So when you go from 3D to 4D to 5D, you see that more low spin complexes. Because the orbital size increases, so the space increases. As a contrast, you have more space to actually interact. As a result, more interaction happens, and this delta value increases. Also, when you have, there is something called pairing energy. I will come. Actually, this pairing energy is like, because according to Hund's rule, there should be maximum spin multiplicity. But when you want to pair two electrons, the electrons repel each other. So you have to provide energy. So the pairing energy also decreases when you go down the periodic table, because if you have more space, then it can accommodate two electrons easily. So that is the thing, that the position of the metal centers, how it defines this delta value. Next, this is actually G factors. There is something called, and this is for different metal. This is actually spectrochemical series, but you don't need to remember all the things. But what the basic message is, that main message, with oxidation state increasing, you get more delta value. Next, of course, how do you determine this delta value? For example, this is a titanium H2O6 3 plus complex, and this is the UV spectrum. And you have this titanium 3 plus D1. So when you put light, then one electron will excite, and as a result, you will get the spectrum. And this value, as Neuber value, this is 20,300 centimeters. It is the delta value for the titanium H2O6 3 plus complex. And this happens actually, I want to clarify, because there is also something called Ian-Taylor distortion. So because T2G is here unsymmetrically occupied, or in the excited state EG is unsymmetrically occupied, as a result, you will have 3 total energy transition. We only see 2, the other is in UV region, we don't see. So that's why it is broad also, and you see solder. But the main thing is this one determines the delta value. Next, spectrochemical series. So I think I told you about this cobalt NH3 3 plus complex. So if you replace NH3 by a ligand, different ligand with different donor ability, starting from iodide to the carbonyl. So you see, you get different delta value. You can measure spectroscopically, and you can determine. This iodide is the weakest donor ligand in the spectrochemical series, and this carbonyl is the strongest donor ligand in the spectrochemical series. But actually, this also I told you, this actually, according to the crystal field theory, OH minus should be stronger donor than H2O. But this crystal field theory does not explain. This MO theory does explain that why it is. So that is probably next class. If you are there, then these are the spectrochemical series. One of the important aspects of crystal field theory. The octahedral transition metal complexes. Next, pairing energy. As I think I have told you already. This is just a little bit detailed written. That's why this pairing energy will actually decrease if you go from 3D to 4D to 5D. Now, exchange energy, I am coming in the next slide. So, Hund's rule of maximum spin number of multiplicity. Now, this exchange energy is actually, this is a constant, and this is X equal to whether it is alpha spin or beta spin. So you can, for the same spin, it is written. For high spin, let's say D6 system, P2G4, EG2 system, exchange energy is 10 kex. If you go, because 5 is actually alpha spin, 1 is only beta spin. So you get 10 kex, and for lower spin, you have 3 alpha spin, 3 beta spin, and you can get this 6 kex. So upon going from high spin to low spin complex, actually you loss of exchange energy is 4 kex. So there is the exchange energy loss And exchange energy, as I called it, for mainly we consider because D4 to D7, there you can have high spin to low spin configuration. So that is applicable here. Now, if you consider D4 and D5, they have both part 10 DQ, 3 KEX, loss of exchange energy. That's why the actually low spin compound, if you consider only the exchange energy concept, low spin compound of this D4 or D5 is difficult. But on the other hand, other factors also determine whether it will be low spin or high spin. Suppose if you put cyanide ligand, which is a stronger donor, you will get this exchange energy will be minimized, the contribution. You will get mainly low spin complexes. Next, actually crystal field stabilization energy. So this is calculated as, let's say this is a D4 system. This is a high spin, and this is when it is high spin T2G, and this is a spherical field. In the octahedral field high spin, you can calculate that the energy is actually, this is 4E. So 3 into minus 4 dQo, this is minus 4 plus 6 dQo. You get this minus 6 dQo plus 4E, then crystal field stabilization energy, you can calculate from the beginning energy minus this energy, you get 6 dQo. Now for the low spin, you have to put 1 P pairing energy because one pairing is happening. That's why you need a term plus P. And in the same way, if you calculate, this is 16 dQo minus P. And for D7 system, in the same way you can calculate for the, actually this is one more pairing should be here. So 7E plus 2P was here. And here actually, basically in when you calculate crystal field stabilization energy, you will not see the P term in the high spin configuration in this way also. But this is how we calculate. And this is the case one from D1 to D2 to D3, 8, 9, 10. And you get all this high spin configuration. This is the crystal field stabilization energy in the same way. But when you have D4 to D7 system, you have again high spin to low spin systems. And you can accordingly calculate that this is the crystal field stabilization energy. Next, I come to high.
So this is might be a very nice question. Where the DQ0, where the notation comes from? Like historical?
Yeah, no, it is not historical. I mean, delta D, actually, there is some formula. I mean, D and Q, they have different formula based on the charge of the electron and Bohr magneton. I mean, there is some special formula, but I don't remember that.
Okay. Okay.
So next, I will be in my research talk. I will be at first starting with this high spin and low spin configuration. So I am explaining here also what is high spin. I think high spin this is actually high spin. HS means high spin, LS means low spin. So the number of maximum spins is high spin, and if you minimum spin is low spin, you can consider. So when the delta less than the spin pairing energy, then it is basically you will get high spin configuration because your octahedral splitting energy is always higher than the lower than the P. So when it is higher than the P, you get low spin configuration. And this high spin, low spin, as a consequence, I want to tell you that because here these EGO2, EG orbitals are filled, here only one for the D7. As a consequence, you get different axial, equatorial bond length will not change that way, but the axial, because here two electron, when you form a complex, because two electron is here, that's why for the high spin case, the axial bond lengths will be more than the low spin plate. So this is what I prepared. If you want me to continue, I kind of blackboard. I can continue, but this is what I prepared for the 30 minutes talk. Thank you for your kind attention.
In the last one, we were talking about by expanding along the axial direction.
Yeah.
Are there complexes in which that symmetry? See, at the end of the day, the molecule wants to drop the symmetry.
Yeah, lower the symmetry. You have to reduce
that EG level.
Yeah.
But I can also split the drop the symmetry by contracting the.
This is Z out or Z in.
Yeah.
So
other examples where you have contraction of the axial bond as opposed to So generally, when we say distortion,
Actually, I think Popper
Some
is,
impact.
I think there are examples.
Okay.
I know there are examples, but I don't remember. And copper 2 plus D9 system, if you consider that is strong angular distortion.
Yeah.
Z out.
But I think there is a long.
Yeah, Z out.
the
But
actual-
I think chromium, I mean, there are chromium complexes, for example.
But maybe if I build on this question that maybe so I'm guessing the bond length is the minimum in the energy profile, but I think the energy profile will be highly asymmetric in the sense the compression is probably steeper energy penalty than
Yeah,
elongation.
compression, I mean, you have basically dz square. When d out, dz square orbital will get energy minimized compared, but when compression, dz square will be higher in energy.
But we are assuming in all of this that the axial bonds do not change, right? Or are we not? We are assuming that.
It depends on the electron occupancy of the because axial will be dz square. So dz, if there is a dz square electron, the dz square, the axial bond length will be longer because more repulsion will happen. If suppose dz square is empty and dx square minus y square is the occupied one, then the equatorial bond length will be lengthened.
Actually, so this whole wall is you can write on it and just try to find there is a marker.
This one.
It should work, unless it's a permanent marker. Yeah, sometimes. No, wait. Yeah, so you can just write off it.
Yeah, can you put the earlier slide, maybe 8 or I can't remember now. If people have questions, you post them. If people start raising.
We've seen all these examples work very well with the origins. Is there some extensive work on have you worked with F-orbital complexes?
My field is not lengthened is the effort. My field is not cover actually F orbital. But if you consider F orbital is deeply seated, this crystal field theory is negligible effect. I mean, unlike d orbital has the prominent effect. But F orbital, as I know from my knowledge, that F orbital they are deeply seated, so that's why it is not affected that much. Crystal field, but still there is. In the book, you will find that the crystal field theory is also for F orbital. That is basically same concept. How I mean the whole concept is that if you along the axis, where the lobes of your axis are, I mean orbitals are.
See, you showed a transition, from the E to G to EG. Yeah, you showed a spectra actually.
Yes.
Yeah. But these are forbidden transitions, right?
Okay, degree transition, this can be, but the number of spins remains zero. I mean, it's delta S equal to zero.
Yeah. So,
But if you consider
I'm
Laporte,
not talking about spin selection. This is a selection on Laporte.
yeah, orbital unit. But this Laporte can also be, I mean, become forbidden if you have metal ligand overlap or due to vibronic, I mean, coupling. So you no longer it is like ideal. There's you can from G to G. It is from that's how it is. I mean, even some forbidden can become because of nothing is perfectly symmetric. As in for octahedral complex, nothing is perfectly octahedral actually. If you consider. There is sometimes there will be most of the cases there will be distortion.
Yeah, we talk about vibronic coupling. How does that work? How does that make this allowed?
This will, I mean, this covalency will split this wave function. I think metal orbital wave function and ligand wave function they couple, and that's as much I know that actually makes them allowed.
You just go to the next slide. And Yeah, see, this case, the example that you have given,
Yeah.
it is octahedral, all right, but it doesn't belong to an OH symmetry point here. Because your
No,
L
no,
is,
no.
yeah. So then what happens? Now you have broken the symmetry terribly. It is not even D4H. Then what happens to the system? Because the example you are showing me is going from very high symmetry of the OH to something that's pretty low.
Yeah.
If you had put L on both sides, then at least it would be still D4H. But it is not even L on both sides. So you don't even have an inversion symmetry on this.
Yeah.
So,
So because symmetry, I think if you symmetry, break the symmetry, there will be different degeneracy lifting. There are different several energy levels will be there. So you will get more number of peaks,
okay.
but you have
The
to,
spectrum will become more complicated.
yeah, you
There
more
are
number
more
of absorption maximum we will get.
Can we go
Next.
Yeah, this next slide. Yeah, see, you are given some equations and everywhere you are divided by this 2. Why are we dividing by 2? What is the significance of
Half, spin half. As much understanding this is equal to plus.
So spin half would give you a total degeneracy of the double state. So it will be 2 as
No, I am not talking about that is plus. I am talking suppose this is a one spin.
Yeah.
Equal to be, it can be I call plus half if it is alpha, or this is minus half if it is beta. So I think this coming from that.
But your system is not a single one electron system. With a one electron system, then you have
The possibility here is that the number of coil, let's say this is D4. I mean, this is, even if it is the concept size that this is D6, let's say this is all are S equal to 0 system overall. But if you consider the total 3 alpha spin plus 3 beta spin, this is how they have, I mean, this theory actually, I mean, this equation, because they have
what you have shown is a spin 0 system.
yes, I know overall S equal to 0
so
system,
spin
but this is how they calculate this exchange energy.
What is the physical origin of this exchange?
Physical energy, it's mean, of course, exchange energy, I mean, that is basically vice versa. If you repel, they will repel each other, right? That's why the Hund's rule also says that because the electron don't like to be paired up, they become, unpaired. I mean, they remain to be unpaired because of electrostatic repulsion. Yeah, but only as I told you, this delta O versus P. I mean, that would have been, but the repulsion, I think as much I know that electron likes to repel each other.
Like charges.
Yeah. So that's why they want to, and Hund's rule also proposed that way, that maximum number of spin multiplicity. And if you, of course, if you have a, I mean, d orbital can maximum 10 electron, because all the 4 quantum numbers cannot be again same. So you can, I mean, you have to apply the energy, but you can make them pairing. Yeah. Kx is a constant.
Yeah.
Mine are questions.
Okay.
Why transition? What is transition?
Electron, it's been transition happens, or a charge transfer transition happens. All the things happens if you consider daily transition or metal to ligate structure transition. That's how this is transition complex. And that is also other thing is that if you call this is S block element, they are now in between. That is, I think, P block element is the right side. So in between, that is if you consider the nomenclature, in between is this 3D, 4D, and 5D. So that's how this is in between the transition. You can consider that way also. I mean, you are transitioning from S to P, but in between 3D. What do you say?
Another one somewhere around is the location of the metal ion in the period.
Yes.
Under that, usually singularity with the elements, not for elements.
Okay.
Exactly. Location of the metal ion in the period. one of the sides.
Okay, I meant that if you, so in general, if you go to, let's say, the 3D10, you can use this Scandinavian, there is, I mean, from Scandinavian, how, even if you p-block element, like you move from carbon to nitrogen to oxygen, the electronegativity is increasing, right? So in the 3D also, like this Scandinavian to this zinc, so that is, you will move horizontally. But vertically.
Simply ionized.
Okay.
Should I give the site in the location?
No.
The statement, I interpreted it that way. Location of the metal ion and the physical.
Of course, different metals will be in the different position. The periodic table. That's how periodic table is. I mean, one same, both the metals cannot be like iron cobalt cannot be in the same position.
That I agree.
Yeah.
I am asking the question. Simply ionized helium. Should I expect the properties to be similar to hydrogen? Where you had mentioned that.
That my meaning was that you where the metals are located actually. That's why you in the same row, same period we go down.
That is what you meant in this perfect statement would have been the ion of the parent metal.
Okay. All right.
Then there is no ambiguity.
Okay.
So somewhere along we spoke about molecular mechanisms in the introduction.
Yeah, single molecular magnetism, one molecular magnetism. Like in the one molecule, it can show different magnetic properties. I will be speaking in my research talk. What is this crossover octahedral complex? So one molecule you can have S equal to 0 or S equal to 1 also depending on temperature. So there are huge application in sensor switches. I mean, I don't work on this application field, but I can tell you the principle behind this application is like we try to characterize and synthesize this complex in the way you get some novel property that might be future used for the broad community of the scientists. And from my research, as you will see, basically synthesis and characterize the properties. So that single molecular magnetism also is like in a single molecule you find not like hard magnet. In a single molecule you study the magnetic properties depending on temperature, heat, temperature, pressure, or light. Depending on different external perturbations, you study the magnetism. That is the thing. And of course, these are, according to the application people, if you have in the hard disk and in the hard disk memory devices, if this single molecular magnetism they can use, but the problem is that the scientists have only reached because this single molecular magnetism behavior, because it is observed below actually near liquid nitrogen temperature. So in order to have practical applicable, they are always studying until this room temperature. But until they also know by theory also it is not possible because of a lot of relaxation. But still they are trying, and also I will see my research talk.
You say theoretically it is impossible.
They still want to make somehow work out of it.
Theoretically impossible, something should not work.
But as my understanding, theory, don't get me wrong, theory is also not the ultimate. Even Albert Einstein's theory has to be proven experimentally. So, I don't want to disrespect anyone.
Somebody in the home, this theory is not.
Yeah, maybe I am not a theoretician, but I don't want to disrespect anyone. But this is the case. Every theory needs to be, even we want to, I had a talk. Because one of my manuscript is waiting along for theory. One of them asked, why you don't submit without theory? But experiment is already proving, theory is saying different. But I would say that theory is not complete in your work, that theory. But in doing experiment, you can achieve something, which then the theory can explain. Both are necessary, but that is the thing, I understand.
Just to support you, I think there is one case in spectroscopy literature that Krea predicted, I think it was in the case of one of the excited states of the hydrogen bomb, that's in plus one. And Krea predicted certain situations, and then the experiment that showed that is not the case. They had to redo the theory at a higher level, and then found that the experiment was right, and their earlier predictions were wrong. So So to that extent, yes, I agree that
Yeah,
both have to go hand in hand. Theory without experiment is blind and experiment without theory is lame.
yeah, it's also depend upon, like my PhD supervisor, he does not believe theory. Even some theoretician also says something. He said, until unless there is experimental proof, I will not believe. But when I work now with postdoc, he totally takes the support of
Do you
theory.
agree with that point of view? I mean, I don't.
I agree with my PhD supervisors, agree that because I have been trained by, but in order to build your career, you also need paper. So you should take the support of theory. But if you ask me,
No, but to
honestly,
say that, I don't look at theory, I just need experiment. Is that point of view?
no, you need theory,
Yeah.
but you cannot also rely heavily. If you ask me now, okay, as an experimental chemist, I will take maximum support of experiment, but I will also take the support of theory to support it. But that is the thing. But of course, you can't rule out theory unless science will exist, experiment and theory will go hand in hand.
Of course, you want to teach this.
Okay.
What will be your strategy?
Hydrogen atom.
That is the element. So these are all the things you should understand to understand the reality. What will they do?
I will start how this arc, which I read this one book, this is a photo of something. They started, right, how this arc was formed and how this gases nitrogen is, how this hydrogen is this, why helium is this, why nitrogen is more, how this arc was formed, then you need hydrogen, nitrogen, oxygen. Starting from that, you need different also elements are present. And into that, this Mendeleev, he proposed this periodic table. Also, he proposed something based on that. In future, people are also, I think, before 2 years also, once something was discovered, still it was put in periodic table. It was not complete. I think what he proposed, it was not complete. Still, some new elements have been discovered, and they are being put in the periodic table.
That is addition. I don't think there was a gap in that English.
No, I think it was, I don't know, there are additions in the terminal when you get right to the bottom.
More elements.
Yeah.
More elements.
Yeah. But he also predicted that there will be some elements discovered and it will be added.
No, I think Mendeleev made a lot of predictions and, at his time, there were only half the number of elements that we know today.
Yeah.
Mendeleev, I think, had data of about 56 elements. Today we know 110, 115, 118, 121. So with 56, he predicted certain things, but left gaps in between. Like for germanium, gallium, and all that, boron, silicon. And I think in the case of even iodine and I think the element before that, he predicted that based on atomic weight, their order was he had to just reverse the order. He reversed the order.
Between mass number and atomic
Yeah.
number.
And in one particular case, he said your atomic weights are all wrong. Go check it again. Turned out to be wrong. So he was so confident about his classification. So I don't know, I was expecting that you would talk about first the classification started before Mendeleev. Periodicity properties. You had Dobereiner's law of triads, the Newland's law of octaves. So I think that was what Mendeleev actually used to, in some sense, to build up the model.
I wanted to ask what this notation T2G why this complex?
Okay, so this is, if you
Can we say high and low?
no. This is like T2GF3. So with the reservoir, this is triply degenerate. One way is that you can put a one electron, it can have maximum, remembering 3 maximum arrangements.
So
T2G and EG is for double. EG you have 2 orbitals. So it can have 2 maximum arrangements. So it is called EG. G is for Girardet because the Girardet is even. So if you consider this, let's say dxy, these orbitals, sorry, might not be perfect. So this is minus plus. If you put a mirror plane or center of symmetry, you do not change the sign. That is well for G.
Inversion symmetry, right?
Yeah.
Okay. Yeah.
But where is the origin actually from? The T2G, BT.
I think this is it is total physical chemistry, this group theory. P2G and EG, it can have T1. It is total physical chemistry, I know. Or in organic chemistry also there is group theory. Based on that, it is coming how much.
Yeah, they are all the abilities to represent
Yeah, yeah.
in that point.
Yes.
That comes from there.
First or second slide, you explain that ruthenium trees between
Yes,
is both oxidant and reductant. Okay.
yes,
How
yes,
will you
ruthenium.
explain that?
Okay, ruthenium, because if you put donor, then it will go down. If you consider a cycle, so ruthenium 2 plus, let's say you have.
Yeah.
Then you have this, if you light, it accept light, it get excited state. It now this transfer either take electron from donor to it get ruthenium plus in this way, reductive quenching, or then you have it provide electron ruthenium plus go back to ruthenium 2 plus, or this excited state ruthenium 2 plus, it actually again give the electron, it go to ruthenium 3 plus, and the ruthenium 3 plus again take the electron, then go to ruthenium 2 plus.
So for if I compare the ground state oxidation reduction potential, the excitation reduction potential, how it will vary? It will be low or high?
No, if it is, this is, if consider, it is giving, taking electron, right? If it, it
Ruthenium
is
is D6, right? Ruthenium 2 is D6, so it will be a low spin.
low spin. It is always low spin for the element. So,
And
so
then it
it-
will have a ground state, let's say ground state oxidation potential.
the oxidation potential actually, the redox potential in, it become negative. So it become, as my
How
understanding.
is related to your 452 nanometer, the reduction? That
If you consider the nanometer to this electron volt, then you will get the energy gap between that.
yes,
It
so
will
it is
excite
plus or minus. I have to add it or subtract.
as you. I think if it is the case that you have to subtract it, minus 4.
So do we got an oxidation or reduction?
If it is minus already, it will reduce because it's strong reducing agent.
But in short, it is also a strong oxidant, right?
No, it depending on this, whether I'm not expert, but donor or acceptor, I know this catalytic cycle, that the acceptor will take the electron, it will go A dot minus, the acceptor dot minus. Then if the ruthenium is electron rich, the donor needs ruthenium electron, and acceptor takes the electron
So it
from
will
the.
happen for every transition material complexes in the excitation. Or
That I am not clear actually. I'm not expert, sorry. I just wanted to demonstrate one example. That this is importance of coordination chemistry. Coordination chemistry.
Just a question. You made a comment, in one of the questions that the f orbitals are deep seated. And when you tell this to students, most of the time they would like to know what do you mean by that. Immediately the answer we give is, you look at the radius distribution and decide. Can you come up with some experimental proof or evidence as to why the f orbitals can be considered to be deep seated and the d orbitals to be more diffuse? That's what we say. Right? The d orbitals are more diffuse, therefore they interact with the and so on. But is there any very clear-cut, sharp experimental evidence that look, this is the reason why I say d orbitals are diffuse, and this is the reason why I say the f orbitals are contracted? So there any way you can? That would convince the student. We should do that. Otherwise, it's only a statement when you say the f orbitals, because there's no way you can see the f orbitals. So you just say f orbitals are contracted, and then you accept it or leave it.
Probably this.
And have you done any? Have you looked at f orbital spectroscopy? Okay. So if you showed the spectrum of that D thing, where was that? Just see that. And yeah, look at that width. It's pretty large. You look at f orbital spectra, they are very sharp. This width is because of the fact that there's a huge interaction with the surrounding. because of the fact that they are diffuse. Whereas the deep-seated or the contracted air pocket hardly interact with the environment. And any interaction, it's lot of the peak, like hydrogen body would lot of the peaks. Okay,
Yes,
correct.
yes,
So if you showed the spectrum of air pocket, like, terbium or dysprosium or whatever on your degree, and compare that to the d orbital spectrum, which is like this, almost all d orbital spectra are very broad. That's essentially because they're interacting with medium.
Okay, sir. Thank you.
Okay, then thank you so much. Thanks for this.